Right, great. Yeah, so hi, I'm Dan Hatton. I'm part of Diamond's data analysis group, where I'm the team lead for cryo-EM data analysis. So as a team, we try and deal with all of eBIC's data analysis requirements. That's from central installations of processing software to developing and deploying automated pipelines for users. So that's what I'm gonna talk about for the most part. So just a very quick outline of the talk. I will start with a sort of statement of the problem of what we're trying to achieve when we're talking about automated processing, and then how we tackle certain parts of that problem at the moment and how we're thinking about tackling it in the future, with some details of the kind of technologies that we utilize in our deployments. And then I'll kind of, the context that I'll be talking about that in mostly is a tomography pipeline implementation that we've recently deployed for use for users. So that's a kind of early stage tomography pipeline that should get users to rough tomograms on the fly as their data collection is going on. And then at the end, I'll just discuss some miscellaneous but connected developments. So the kind of statement of the problem. So at eBIC, there's a total of 8 microscope systems, and that's 5 Cryoses, 2 Glacius, and a Talos if you include the Cryos and the Glacius from the industrial side. So what we ideally want to be able to do is process data as it's acquired, whether in single particle or tomography, as fast as possible to give the user some feedback about how their data collection is going. So the first challenge that we have is the data is collected onto the detector computer, which is kind of firewalled off from Diamond's actual file system, where our compute resources have visibility. So the first thing we need to do is get data from microscope systems to Diamond systems, and then shove all of that data into processing pipeline and get the throughput high enough that that the processing can keep up with whatever the acquisition rate is. And you want to ideally be able to do that in the scenario where you run all of your microscopes flat out at once, which is rare but possibly happen. Yep. So we need, and then in terms of the pipeline itself, the auto processing pipeline, we want to make some system that is the kind of standard, like buzzwordy things like robust, extensible, and scalable. And it has to be able to adapt to a highly variable workload. So that's both in terms of the heterogeneity of the compute requirements of the individual applications in the pipeline, and also in terms of highly fluctuating data rate coming off the microscopes, as the acquisition isn't, the rate is not constant. And we also need to provide some visual feedback to the users in a useful format. So to address the first issue that I was talking about, which is kind of data transfer, at the moment, what local contacts at eBIC will do is run transfer scripts that just rsync data from the microscope system to Diamond system where it can be processed. They have to start those scripts for every kind of session within the visit, which is becoming more of a problem with things like multi-grid, where the grid will change and you will get a new session that needs to be copied over, and we want to do all of that automatically within a visit so that the data lands on the Diamond file system as fast as possible. So we've developed a tool that's called Murphy for doing this data transfer. So what it basically does is it just monitors stuff on the detector PC, starts rsync processes, and then it can monitor the rsync processes themselves and trigger data processing based on what it sees. So it sees a file has been rsynced over to the Diamond system, and it can immediately trigger the motion correction for that movie, for example. So the architecture is there's a client that runs in the microscope system, and there's a Murphy server which is running on our storage server, which is where the rsync it's the destination of the routing process, and then that Murphy server, because it's within the Diamond network, can communicate with our like laboratory information management systems and processing systems. And then another thing that it does is basically scrape files from the output by the acquisition software to try and capture as many of the parameters that are needed for processing as possible. So the idea is to have minimal user input. Ideally, your local contact would basically just start the Murphy process, and data would be transferred and start to be processed without any user input. Yeah, so now I'm going to move on to how we actually implement the kind of the processing side of that once data has been transferred. So I pulled this this kind of comment on computational landscape scientific algorithms from a SNOMAS report. So SNOMAS reports are written every few years in the US. They're written by the particle physics community, and they cover a wide. They basically try and capture the state of the field. So this is pulled from one about computational stuff. So they kind of talk here about there's two types of computing that you need to tackle. There's either high performance computing or high throughput computing. High performance, you're typically doing one massive task. So you run on many nodes with some communication between the nodes, so that because everything's working on a single task. And then high throughput is when you have a case where you have many independent computational work units, so the parallelization doesn't really require any communication. So in this case, they're kind of talking about individual applications, but you can view it on the macro level as well. So think about the pipeline as a whole, and it's mostly a high throughput problem. You want to motion correct as fast as you can, do CTF estimation as fast as you can, but then it gets more complicated when you go to something like doing reconstruction, where there's some aggregation step involved. So if you are tackling the high throughput problem, there's various ways in which you can parallelize the problem. So for example, you can just have a single application that receives some batch, and then the application just handles everything using either threading or separate processes. Or you can just schedule like a large number of jobs straight to a HPC, or the route that we've chosen to take is you can write services and then have multiple instances of the services running, which gives you some scalability, and there's a lot of tools that I'll come on to for doing that kind of thing. So the basic demography pipeline is just to do motion correction. We do motion correction in motion core 2, CTF estimation, CTF 5 and 4, and then alignment and reconstruction in RTOMO. So Anna from the data analysis team has been leading the technical side of this work with the sort of science input coming from Andy and Dave. So here I've drawn a kind of very simple graph, which just has these applications on these nodes and then some dependency connection between them. But actually the situation is sort of considerably more complex than that makes it look, because you have to, for every movie you motion correct, you then do CTF estimation, so that's like a one-to-one. But for reconstruction, you need some kind of aggregation. You need to have motion corrected the entire tilt series before you do the reconstruction. So this is a kind of many-to-one problem. So what we want to do is take this kind of abstraction and then map it onto some sort of software tooling. So what we've chosen to do is take the vertices and turn them into services. So this basically like a little, kind of like a little server that's running and waits for messages, and when it receives the messages, it does whatever the message is requested. So for motion correction, for every movie, it will receive a message requesting the motion correction of that movie, and it will motion correct it. So it's designed so that each vertex is operating on the smallest possible unit of input data, so that you can get high throughput as acquisition is happening. Yeah, so then what do you do about these kind of messaging parts, these edges in the graph. So for that, I'll go to a quick detour on talk quickly about message brokers. So a message broker is basically a server that listens on some like network, some network connection socket, and receives messages, and then based on a labeling of those messages that you've given it, routes the message through some kind of routing topology to end up on a queue or multiple queues. Those queues have consumers that subscribe and consume messages off of the queues. And one of the key things is that the broker retains copies of messages. Well, you can configure it to retain copies of messages until the message has explicitly been acknowledged by the consumer, which means that you can, for example, one of your consumers might be a motion correction service that runs Motion Core 2, and you can acknowledge the message if the return code from Motion Core 2 is successful, and you can negatively acknowledge it if it was a failure, and if the service crashes during the run, the message broker will have retained the message. So when the service comes back, that can be re-injected, so you don't lose processing information. And you can explicitly negatively acknowledge messages and send them to a dead letter queue, so that you can have a look at them and re-inject them if you think that they're just there because of some hardware blip or something. So we use a message broker called RabbitMQ here. So these services are written in a kind of package called Zocalo, which was developed by the MX data analysis team, predominantly at Diamond, and that has nice methods for communicating with the RabbitMQ message broker. So we map the edges to this message broker. What that does, so that deals with the case where, so from before, you have these more complicated edges. This can pretty easily deal with the case where you have, for example, a single input and you want to route it to multiple outputs. So this would be the message broker can just send it to multiple queues. You have a bit of difficulty with these kind of aggregating edges where you have multiple input data and you want to aggregate that. So, for example, all the tilts and then aggregate them and request reconstruction. So to deal with that kind of thing, you need some sort of state to keep track of where you are in a given tilt series. So has the whole tilt series been acquired, and have all of those movies been motion corrected? And so for that, we send messages back to the Murphy server, and then Murphy decides when it wants to request reconstruction. So we also want to be able to deal with different kinds of data collection schemes. So this is meant to be a kind of traditional tomography data collection scheme where you're collecting each tilt in a tilt series. So you want to do motion correction on each of those, and then reconstruction of that tomogram, and then you repeat for a new tomogram. But with kind of beam shift stuff, you can now collect multiple tomograms in parallel, and you get quite a different profile where you're doing all of this motion correction, and then you suddenly have a bunch of tomograms to reconstruct pretty much at the same time. So you want some kind of thing that will scale based on the workload at the time. So luckily for us at Diamond, we have an on-premises Kubernetes cluster. So Kubernetes is it's a container orchestration system. I'll talk through a bit now, kind of what it gives you, and yeah. So this picture is meant to be, each of these hexagons is like a node in a compute cluster, and then you have a Kubernetes control plane which has visibility of all of those nodes. So you might deploy containerized applications on these nodes. So Kubernetes originally was developed by Google, so there's a lot of web. It's kind of designed for the web space where you'll have like some front end, some back end. They need to communicate with each other. Kubernetes will do things like it knows the IP addresses of where these things are running and can help them communicate with each other. but you encounter a problem if you're trying to run long-running services, where if you have a hardware failure or just a crash in the program, the server will disappear. You'll lose that application. And Kubernetes is designed to be tolerant to that kind of fault. So it will bring the application back on another node and correct all of the kind of IP information that it has about these things if it sees a failure. So what you do is when you deploy these applications in things that in Kubernetes are called pods, you set a replicate set size for the pod. So you can say for this blue application, I always want 2 running, and for the orange, I always want 1 running. And if it has the resources, it will manage that. And then another, so it has a bunch of like DevOps tools involved in it. So you can do very quick rollbacks of applications if you introduce some kind of catastrophic bug into the latest version of a piece of software. You can very quickly roll back and very smoothly roll back. But one of the other things that it can deal with is horizontal auto-scaling. So basically it can dynamically update the size of the replica set based on some metric that it reads in. So typical, well, the kind of standard metrics that it uses are things like CPU and memory usage. So if some application is taking up a huge amount, is using a huge amount of memory resource on a single node, it can scale up another service to try and take the load. But one of the things that Anna's worked with the cloud team at Diamond to do is get us get the route and queue length basically added as a metric for this. So if messages start building up in a queue for a particular service, it will auto scale the service and deal with the backlog. Yeah, so the whole tomography pipeline is kind of deployed onto Kubernetes, communicating through the message broker, which can, and then messages also get sent to an eBIC processor service, so that then connects to eBIC, the laboratory information management system, putting in processing information, and Murphy can also communicate with this to sort of register data collections and things like that as soon as they happen. So now just a quick thing about some slightly different work that's been sort of trying to develop a SPA pipeline, which Matt mentioned has been rewritten in the CCP-EM pipeliner, which the flexibility of that allowed us to make some quite significant efficiency improvements in terms of our cluster resource usage. But that Stephen, who's recently joined the data analysis team, has been working on some extensions to this pipeline. So, for example, adding the rely on 2D class auto selection after. So we process 2D classes in batches of 20,000 particles. So you can sort of, and then we at the moment do 3D classification on the same batches of particles, but you can kind of slot the 2D class auto selection from rely on in the middle of that, and rebatch out the end of that. So here's an image of some data courtesy of Dave. So the image on the left is the best 3D class in a particular batch without the 2D auto selection, and then on the right is with the 2D auto selection. So here it kind of picks up about an angstrom resolution, and this is hopefully kind of a more useful thing for people to be seeing on the fly, and it also saves us some compute resource. Obviously, this is a single case where we found it works quite well. Sometimes it has no impact, but we've never seen a case where it makes things worse. So you at least save some compute resource. And then another thing that Stephen's been looking at is whether we can determine the particle diameter without having any kind of particle diameter input from Crayola picking, because when Crayola picks, it gives you the diameter of each pick. So you can kind of look at the distribution and try and pick a value that you think is good. So that kind of builds towards the aim of having the automated processing happening without any user input. So now quickly onto visualization tools. So Guilherme in Diamond's LIMS team has been building a new front end, still using eBIC as the database in the back end, but a new front end for both SPA and tomography, auto processing, visualization. So the software stack is Fast API, Python backend, React front end. So I think that's essentially what what Doppio uses. So these are just some tomography pages. So here you have motion corrected movies, CTF, and then down here some stuff to do with the tomograms. So all of this will update as the processing happens, and you can page through individual tilts in the tomogram here and page through tomograms at the top. There's some 3D visualization of the tomogram, so you can basically just scan through the Z-axis. And he's also re-implemented what we have at the moment, which is SPA processing view in SyncWeb. He's re-implemented all of that and added a viewer for the 3D classes. And then another kind of miscellaneous thing is something that Kyle Morris, the senior scientist at eBIC, has been working on, which we've helped him with a bit, which is trying to gather some metadata, both from the EPU outputs and from a processing pipeline, to look at, well, these various things. So here he's plotting collection rate as a function of mag, and you can do things like look at how different bags do their data collection differently and how that affects things like data collection rate. And then he's also talking to CCP-EM about how this kind of information could be used to automatically populate parts of depositions, and he produces these session reports. You can produce these session reports for users, which tell you something about some simple summary of your data collection, the parameters you used, kind of how many shots you were doing per hole, that kind of thing. And we're currently planning how to integrate that further into our information management systems, to make it like searchable and things like that. Yep. So well, that's it from me. Just many thanks to all the people in eBIC who help us, and everyone in the kind of wider Diamond computing teams.